Welcome back. We're in the last three classes of the term. Today and next week we're done. So this, I've got more recent pictures of Dora, but this is an old one. It's, we were out in this area just recently. It's McIntosh Run, single track trail. It's out in Spryfield, not far from J.L. High School. And the down below it is Colfax Lake, and in the far distance you can see St. Mary's Loyola. It's a really lovely spot. Anyway, let's get going. So the last test is going to be on Friday. I'll do a couple of practice questions in a minute. You've got a quiz on Saturday, and then there's only one more after that. People can contact me because they missed one or two quizzes. Remember, I take the best 10 out of 13. There's 12 chapters plus there's a quiz on the course outline. So, but if you've missed one or two, or even three, it may not really affect your grade significantly. The course feedback survey, I'll put a reminder. If I don't get it done tonight, I'll do it tomorrow. Try to get a few more responses. We're up to about 85 now, which isn't too bad. That's only 20% of the class, but it is probably a good representation of feedback on things. And you'll probably get an email that will provoke you about something else about the way the course was done. And see if that'll stimulate you. The course evaluation, we tried to do that in person on Monday, and it didn't work. They didn't have it set up properly, it seems. So IT was working on that most of yesterday. I've got messages back say they have appear to have resolved the problem. So please go and try doing that. I appreciate it. I want actually more on the feedback survey than on the course evaluation, but at least with your other courses, do the course evaluation. We need it for performance evaluation of our faculty members. Friday, I'm sitting on a panel to review promotion applications by a couple of faculty members. I haven't dug through their dossiers completely yet, but I think we're going to have trouble because we're missing any substantive course evaluations for the last 2 to 3 years. And that makes it really difficult to be able to evaluate our data teachers. So it's really important for us to do those performance reviews. And those do come back as feedback to the interim. Anyway, one more week and we're finished. Let's get through this week then. Oh, again, I've told you feedback survey is really important. I've got a bunch of questions. 2 of them, I provoked you before about should we have a final exam? Done with final exams. But I've got 2 in particular. I'm using Top Hat. The university doesn't like me using Top Hat because it's not officially approved by the institution. Although you're seeing other platforms being used by Pearson and others that have textbooks, they want me to use Brightspace, and I can't do a number of things we've done using Brightspace, not as Top Hat is ease of use for me, but as well, for example, in your chapters, I've embedded questions within each chapter that you can do, and you can annotate your chapters, and I can't do that to the same. I can't embed them within Brightspace. Testing has to be completely separate from documents, but also I don't think you can annotate your documents in Brightspace the way you can in Top Hat. I don't know if you've been using the feature in Top Hat. Anyway, I do need that feedback. I've been trying to push the university to get a site license so that at the very least you don't have to pay the access fee, but so far no luck. I've been very flexible with some of you to do with late missed tests, assignments, that type of thing. and giving opportunities to get them done, because it's just too many points to throw away. But does that affect the integrity of grades? During the pandemic, people really appreciated that because they were under a lot of stress. That's over. What about now? Is something that should be continuing? Is it a good idea? So I'd appreciate your comments on these sorts of things. Anyway, let's do a few questions here. Now, this is getting into naive Bayes, but it also relates back to probability that we did before. And some of these you might have to, if they were on a test, someone looked them up, take a bit of time. So some of these you wouldn't be able to just pull off the top of your head. So which of the following is Bayes' rule? Probability of A and B, probability of A given B, and probability of B, or probability of A given B is probability of A, that should be and B, divided by the probability of A. Probability of A given B is the probability of B given A times probability of A divided by the probability of B. Okay. Or none of the above. Oh, boy, a lot of formulas here. Okay, so let's go through these. The first one is sort of like Bayes' rule, and Bayes' rule you can derive by following a rule sort of like this, but it's our multiplication rule. Chance of A and B happening together is A given B times the chance of B. So you would use that with a tree. You're starting out with B, and then you're branching on to A or not A from B. And then what's the chance of B having A and B? Following those two branches out there. That's implicitly what you use when you're doing that probability tree. Okay, so that one is fine, but it's not Bayes' rule. Probability of A given B is probability of A and B divided by the probability of A. Actually, that's wrong. It's nothing. It's not a variation on the multiplication rule. If you brought that probability of A over to the left-hand side, you'd have probability of A and B is equal to probability of A given B times probability of A. No, it's not lined up. If it's A given B, it has to be times the probability of B. If it's B given A, then it's times the probability of A. So this one has got it confused. So B is not true at all. It isn't a formula. Okay. C, that one gets complicated. It's A given B is B given A times probability of A, and then all divided by the probability of B. And so if you took that probability of B and took it to the left-hand side, you would get A given B times probability of B is equal to B given A times probability of A. Those match up properly, actually, and both of them are saying the same as the probability of A and B. You can understand that. But actually, this thing is Bayes' rule. Bayes' rule is a rule for flipping B given A into A given B. So flipping the sequence of those. So C is correct. Try another one. If the events A and B are independent, which of the following is false? Okay, so three of them are true. Watch it. If they're independent, if A happens, then it'll have no impact on the chance of B happening. That's exactly what independence means. It doesn't prevent it from happening. That's mutually exclusive. But it has no impact on its likelihood. So knowing A gives you no insight about B. It has no information. So if they're independent, one of them has no information but the other. B, if A happens, B cannot happen. If they were independent, no, because if you know A, then you know what's going to happen with B. B won't happen. So knowing A tells you a lot about B. That This answer, if A happens, then B cannot occur, is a definition of mutually exclusive. That A and B can't happen together. C is probability of A given B is equal to the probability of A. So knowing B doesn't change the probability of A. C is correct. C is basically the same as A, but stated mathematically. The third choice, probability of A and B is probability of A times the probability of B. This is actually true. That usually it would be the probability of A and B would be the probability of A given B times the probability of B. But the probability of A given B is the same as just the probability of A when they're independent. C is correct. So D is actually the multiplication rule for independent events. It's maybe a tough question, unless you recognize that B is completely wrong. Okay, naive Bayes. What naive Bayes? It assumes that the predictor variables are mutually exclusive. It has similar data limitations to decision trees. And can result in probability estimates that exceed 1. And D is none of the above. The naive Bayes is a simplification of Bayes' rule for a complicated problem where there are two events, but maybe a whole bunch of them. We're trying to predict A given a whole bunch of other things. It does not assume anything about mutually exclusive. It assumes the predictor variables are independent of each other, that they're unrelated to each other, but they are related to the target. So if we're trying to predict that you're going to renew car insurance, those other variables are related. They affect the chance you're going to renew your car insurance, but they're unrelated to each other. Gender and age aren't related, or other types of things. Does it have similar data limitations to decision trees? No, it doesn't. Because we made that simplifying assumption about independence, it allows us then to calculate probabilities using a log without having to split our data up into different groups, because we don't have to look at them all together. We can look at them separately for different variables. And so B is not true. Can result in probability estimates that exceed 1. No, it doesn't. That happens with linear regression, but with the other rules we use, no, it's not dealt with that. So the answer is actually none of the above. That's it. Lift. What is lift? Lift is something that we came across in naive Bayes. It's the same as a correlation coefficient for binary variables. It's sort of, but it's different. It does give you, correlation gave you insight. So if a correlation is higher, it means it's high and it's positive. Then knowing one thing gives you a lot of insight into the other one, that go up together. Or if it's negative, they go down. Downward sloping relationship. But this is somewhat different. Lift increases the probability of a target outcome. Sometimes it does, sometimes it doesn't. If the lift is bigger than 1, it does. If it's less than 1, it doesn't. It makes it smaller. It ranges from -1 to +1. That's what correlation coefficients do. But lift is always bigger than 0. Can't go negative. It reduces the probability of the target outcome if it's less than 1. That is true. The lift is less than 1. It means that the target is less likely to happen. The smaller the lift is, the less likely it's going to be. Okay, if it's less than 1. If it's bigger than 1, then it scales up the probability. We multiply by lift. So multiplying by a number that's less than 1, you get a result that gets smaller. Multiplying by a number that's bigger than 1 gives you a bigger answer. So lift can push things up, it can push things down. And it can push it down if the lift is less than 1. D is the right answer. Those are rule 5. Right. Those are ones from tests that I decided not to use yet. They were a little bit too tough. Last class, we noted that success or accuracy was made in terms of percentage correct in depth classifications. So I gave you 5 measures. Accuracy, percentage of correct classifications. How many answers did you get correct on the true false test? Sensitivity was the percentage of positives correctly identified. So among those that renewed their insurance, how many did you predict? Or how many of the good guys did you identify? That specificity looks at the negatives. Of the negative ones, how many did you get right? So of those that didn't renew their insurance, how many did you identify correctly? And if it's negative, was a bad outcome. How many of the bad guys did you catch? False omission rate. So these other 2 rates that we frequently look at focus on the mistakes you made. So false omission rate, they were classified as negative, but they were actually positive. So you thought these people would not renew. You predicted that they would not renew their insurance, but actually they did. So you got them the wrong way around. Okay. That, or you thought they were bad guys and actually they were innocent. So that's something that often we're quite worried about. You don't want that rate to be very high. You don't want to send innocent people to jail. But that's sort of similar to a false omission rate. That's a type 1 error in statistics, something you'll learn about next year. False discovery rate. Percentage that were classified as positive that were actually negative. So you thought they were going to renew. That's what you predicted, but they didn't. Okay. You thought they were good, but they were bad. You thought they were valid transactions and they were fraudulent. You made a mistake in that regard. But these were ones where we thought someone had cancer. Mammogram came back as being positive, but they really didn't have cancer. Made a mistake. Got the poor patient scared to Jesus. Okay. So we could, these I had summarized in table. Tables generally have the columns being the truth, what is the right answer, and the rows being your predictions, what you thought would happen. And what you put in the first column, we usually view as being positive outcome, and in the second column as the negative outcome. So maybe positive would be a valid credit card transaction, and a negative would be a fraudulent credit card transaction. But for medical tests, for example, like COVID test, we think of a positive test result as being the thing that you're looking for. So what you're searching for are the good ones, or the people with COVID, and a negative result is people that don't have COVID. So this positive, negative, you have to be careful. How did you define what is positive, what is negative? Okay. And you would take an action. If your test came back as a positive test, you would say, oh, you've got a quarantine. And if it came back as negative, you'd say, oh, you're good, you can go on. But in both instances, we could be wrong. Hopefully not too long. That with the insurance, we thought of a positive outcome would be renewing your insurance, and a negative outcome would probably be someone who's switched. They still got insured. They probably switched to a different insurance. And with each one, there may be some action you're going to be taking associated with that. If you predict they're going to renew, what do you do with that customer? If you don't think that, you think that customer is going to leave you, it's customer churn, they're going to switch to someone else. Are you going to do something? You're going to reach out, offer them incentive, do something? Anyway, how do you deal with that? So that positive, negative, though, is up to you. But once you define what is positive and what is negative, then that defines what sensitivity or specificity. Sensitivity looks at positives, specificity looks at negatives. So what did you define as being positive or negative? And the false omission rate and the false discovery rate have to do with the mistakes about how you classify things as positive or negative. But it makes a difference in explaining what you've done. That and trying to decide how do you make decisions, because you've got to make decisions in the end. And if you're using different models that led to potentially different decisions, all the models will make some mistakes, but they may be making different mistakes. They may be better at sensitivity, but worse at specificity, or vice versa. That which model should you pick? Do you want the one with the highest accuracy? Maybe it's the one with the low false discovery rate. So that there's a very small percentage of loans that you approve that are actually bad, or a very small number of people that you quarantine that don't have COVID. Maybe it's a small number of people that you sent to jail that were actually innocent. And in a field called hypothesis testing and statistics, they focus on having a very low false discovery rate. That a false omission rate, that would be having a small percentage of rejected transactions that were actually valid. That, or with the COVID one, the way we had it set up, it's a small number of cases that you thought were okay. They got a negative test, but they actually had COVID. That's serious, okay? So what are you interested in? Catching the bad guys? That they're different measures. And maybe there's one of those stands out as being so important to you that you're going to pick that performance measure as the top one you're going to focus on. It doesn't mean you ignore the others. There are some decision-making frameworks where you put limits on how high or how low or something some of those measures are allowed to be. And then within those constraints, you've got one other performance measure that you're going to try to find the minimum of. Sort of like you did one, you did linear programming, you pick one objective, say profit, to maximize, but you put constraints on what you're allowed to do. So if you put environmental constraints within these environmental restrictions, how they make most money, so that you try to balance your thoughts on dealing with the environment versus making a big profit. Or maybe you set a minimum profit goal, and then to achieve that level of profit, what action should I take to minimize the environmental damage I can create? Okay, so we can flip things around different ways. So there are ways of doing it, but it's hard making a choice. Okay. But it's hard. Which one should you be picking out of all of these different things? And as noted before, the last class, these are issues and interpreting problems different ways. That I introduce you to pivot tables, and do you want to look at percentage of column total or percentage of row total? What's important to you? Maybe you want to look at both. Depends upon the application. And then we looked at it in probability. A given B or B given A. Which one do you want to do? Here we're doing the same thing again. All three problem instances are the same material, but we're using different language with them. And just like I've told you before, very smart people make mistakes. they get confused on this stuff. And I covered the topic 3 times now. Out of 24 classes, focus of 3 of the classes, on the same topic at different intervals of course. And you still probably don't have a good handle on it. Because it's hard. It's worth repeating over and over again. That they don't come easy to you. Right? But is there an alternative to all these things? Well, a very popular measure is used when you're making very repetitive decisions. So if you're wrong sometimes, you're right a whole bunch of other times. And you're more interested in the average performance. And trying to decide, well, what's a good average? Maybe put it into terms like money and maybe expected monetary value. Maybe that is an easier way to make it more visible to you. So let's do a few simple questions to introduce what I mean by expected value. So this has got no decision model in it right now. I've got the idea of a marketing promotion to send out to customers. It's going to cost me 10 cents per customer to get this out. Maybe I'm using a third party that's doing the marketing. If they buy the product, I'm going to make $15. Okay, I'll not only cover my costs, but I'm going to still have $15 in my pocket. But if they don't buy it, I've just wasted 10 cents. I'm trying to recruit them. And suppose there aren't that many customers that really want to buy it. Maybe there's only 1 in 100. Okay, is this promotion really a good idea? Well, we could look at, let's make it more concrete and that not treat this as probabilities again. Let's look at imagining sending it out to 100,000 customers. How much money would I make? So out of the 100,000 customers, I'd expect 1,000 to buy it. And I'd make a profit of $15,000 from them. But there's 99,000 that I sent a promotion to that didn't buy it. And I lost 10 cents with each one of them. That adds up to almost $10,000, $9,000. But I made 15, I lost 10. I'm still ahead $5,000. Or on average per customer, I made $0.051, but 5 cents per customer. Now, obviously, with each customer, I either made nothing and actually lost money, or I made a profit of $15. I didn't make 5 cents from any one customer, but I can average out customers as a whole. And on average, it works out to be profitable at 5 cents per customer, just spreading it across all of them. So it looks like a good idea. This approach I took is what's called expected value. Mathematically, it's written usually as a capital E for expected, and then of what the variable is. And so profit. Okay. And how I calculate that, I take each outcome I could get, those are values of X, times the probability that that outcome arises. And I'll add them up. If there were many different outcomes I could have, then I'd have to add up all of those. In this case, I've got just 2, but in practice, we can have many different outcomes. So my expected profit is going to be $15 times the probability, that's 1 in 100, plus, well, minus $0.1 times 0.99, the chance they don't buy the product. And you calculate that through, and you should get do I have a small place here? I think I do. Yeah. It should end up being 0.51. Yeah, I got a typo there. So we call it the expected value of a variable for the decision. What happens on average? And it's what we just had a second ago. That if you look back to what I had before, I just, instead of putting a probability, I had 1,000 here and I had 99,000 there, and then I divided it all by 100,000. So 1,000 divided by 100,000, and 99,000 divided by 100,000. The same as what I did just a minute ago. And this is the most widely used measure for performance of decisions under risk. So let's look at a data mining example related to this. I send the promotion to everybody. Maybe I could use a model to predict who are the ones most likely to buy my product and who are the ones least likely to buy it. I'm not going to send this promotion out and spend even 10 cents on people that I'm pretty sure will not buy it. So let's suppose I had a model and the model said, no, don't send it to 100,000. Just send it to these 2,000 customers that the model predicted I should send it to. And analyzing historical data on people purchasing, if I'd used that before with past customers, my model would have said send it to 2,000 of them, and 900 of them would buy it, and 1,098 would not. Not great. A lot of the people I sent it to didn't buy it, but I got most of the ones that did buy it. So I'm not sending it to 98,000. So they're not going to buy it because they don't know about it. And I'm going to miss out on 98 people that would have bought it if they received the promotion. But I'm not sending it to almost 98,000 that we're never going to buy it in the first place. So is this a good idea? Well, you can look at what's happening here. That if I send them the promotion and they buy it, I make $15. If I send them the promotion and they don't buy it, I lose 10 cents. Okay. If I don't send them the promotion, I don't make any profit. I don't have any loss. 0 and 0. So take each of those outcomes, multiply by their probabilities. So I've got 15 times a tiny, tiny number. Oops. And I've got minus 10 cents times a very tiny number. Don't worry about that. What do I get? I get 0.1342. It means on average, I will make almost 13.5 cents per customer. That's a lot better than 0.051, better than 5 cents. So it's much better. That my classification model correctly identifies most of those that are going to buy it. And it correctly identifies almost everybody that wouldn't buy it. So the sensitivity was pretty good, 90%. So I've gotten most of the profit of it. And my specificity is actually very good as well. And so I've avoided most of the losses. So it's a good model. So that sensitivity and specificity are quite attractive. I'm getting most of the good outcomes. I'm getting very, very few of the bad outcomes. The net effect, so I'm going to make more money. Okay. Now, in that one, actually, of the 4 boxes that were in my table, only 2 of them had money associated with them. You could have problems where all 4 boxes have money associated. Let me show you a different one. Let's suppose I'm trying to predict my credit card issue. Remember that one that we had before, that I was trying to predict whether or not the credit card transaction was valid or fraudulent. And I was very good at predicting that if I approved a transaction, more than likely it's good. So I had those customers really happy. But I rejected a bunch, and there can be consequences. They're going to be very unhappy because made a mistake. There's a whole bunch of different things that are going to happen here. So what have I got of the different? I've got 4 outcomes here. So let's look at a valid transaction that gets approved. When I do that, that transaction, say it was purchasing something for $500, that the merchant is going to pay me a commission, probably 2.5% or so. So 2.5% of 500, it's what, $12.50, I think, altogether. I'm going to be making as fees to the merchant for being doing that. Also, the person that bought it for $500, they will not pay it off right away. They're going to carry it on their account and spread the payments over the next couple of months to pay it off. So I'm going to make interest on that end. So purchase amounts vary quite a bit from small ones to big ones, but maybe on average I make $12 out of interest and fees per transaction. So proving a valid one is very, very profitable to me. Now, fraudulent transaction, though, if I approve it, I've got to eat the loss. The customer is going to say, hey, I didn't do that. And so what's the average loss? Those fraudulent transactions are probably pretty large in many instances. Let's suppose it's $500 on average, and I have to pay out that money. Now, if it was a fraudulent transaction and I rejected it, then that's great, because then I didn't make any money off of it, but it was fraudulent. No wonder I wouldn't make any money. But I also didn't lose anything on it, so it's zero. What about a valid transaction that I rejected? So I rejected it, so I'm not going to get any fees or interest on it. I'm going to get a very upset customer that might end up thinking twice about using their credit card in future and might actually decide to switch banks and use someone else's credit card. What's that worth to me? Now that one is more difficult. I don't have data to be able to come up with the number. Let's just put a number on it. Let's say it's $50. It's about 4 times as much as we make on good one. Okay, so I'll just penalize myself. $50. I'll send them a gift card or something. So what would be the expected profit per transaction? I can calculate it. I've got $12. I approve most of the valid ones. That's 98% of all transactions. That I lose $500 on the 2 and 1,000 that are fraudulent transactions that got away from me. I didn't catch. I'm going to lose $50 on close to 10 in 1,000, almost 1 in 100 that I reject. That is really good. It's a valid transaction, and 0 on the fraudulent ones I catch. Net effect, $10. Hey, I'm making money. But last time I suggested, even if the performance looks good, what if I did nothing? I didn't use the model at all. So is $10 good? $10 compared to what? That if I didn't do anything at all, would I actually be like losing money or not making money? If I didn't use my model, I would probably be approving every transaction because almost all of them are good. And my expected profit would be, well, 99% of them are good. And I make $12 off of each of those. 1% of them I lose $500 on those. Yeah, I still make a profit of almost $7. So even if I did nothing, if I approved all transactions, it's still profitable to me. This credit card business. Credit cards are a profitable business. But it would be even more profitable if I used a model to try to guide me on which ones I should approve. I shouldn't approve every transaction. So the model works. Think about the numbers in the formula. So I used data from the past about that I had 1 in 100 transactions being fraudulent. And I've got performance data on my model as to how many valid ones it approves and how many fraudulent ones it approves, and everything else. So the probabilities and the model characteristics I might be reasonably comfortable with. But what about these dollar amounts I put in here? Where did they come from? My accounting information system, I should be able to work out how much profit I make on average per valid transaction. Some of them I make a lot, some of them I make a little, but I'm maybe I'm just going to look at what's the total income I've got in the last year and divide it through by all the transactions that I processed in the last year. So my income paid from fees from retailers and interest from customers. And I just divide through by all my transactions. And I get the $12 figure. Okay? A crude way, anyway, of getting something. The fraudulent ones, again, I could look, okay, I had, a few thousand fraudulent transactions this year. What was the total amount of losses associated with them? What's the average per transaction? I've got the data to put out average figures, and this model is built around using averages. But what about the $50 for loss of goodwill? Anytime I get a fraudulent transaction that, a valid transaction rejected, I don't go and send a $50 gift card to the customer and say, I'm sorry, that I'm too cheap for that. But what is that goodwill worth to me? I don't know. I just made up a number. But what figure should they use? Maybe the real value of a customer is more than $50. Maybe losing a customer is worth $100, $300. There's a real risk I'm going to lose them. And even if I lose a small percentage of them, if the lifetime value or at least annual value or something of that customer is significant, then maybe I should think about using a different figure. So you could try doing sensitivity analysis. You may have done that in Quant 1 when you aren't sure about some of the numbers. So I could have gone back, let's try it with $100 then, $200, $25. Look at different figures and see what happens. You can do that. You can also, if there's only one thing in a relationship that you don't know, you may be able to explore that one in more depth. So I've got using my model where some transactions are rejected, but most of them are approved, or not using a model at all where I approve every transaction. That baseline case makes a profit of $6.88. Using my model, how much do I make? I'm not quite sure on average because I don't know what goodwill is worth. But I could put those terms in there and leave goodwill as an unknown. So I put it in there. I've got one unknown in an equation. I can rearrange and solve it. I rearrange and solve it, and I get goodwill is $392. Whoa, that's really big. Upsetting a customer on average is worth $392 to me. So I'm not going to upset customers, but now I know what they're worth. If I don't think the cost to me of upsetting a customer is like $400 or more, then my model is good. If I think, no, upsetting a customer might well be worth on average more than $400, then I should have just approved every transaction. I'll find a better model. But this gives me an idea. And sometimes with some variables, we don't know their value. We can't estimate them and measure them all accurately or numbers that we're comfortable with, ones we can justify. So we can use sensitivity analysis to put bounds on it, say as long as it's below this or it's above this, then we should do certain things. Anyway, that may give you a lot of comfort with repetitive decisions. Don't worry about the individual. That look at the average, look at the big picture. Don't worry about the little people that you're hurting. Yeah. Well, what about if it's you that's being hurt? You're thinking of it from a different perspective. The customer sees it more as a one-time decision, okay? Because they don't get the opportunity to average things like a big bank with millions of transactions. That individuals are often making one-time decisions. And although we may not be using data mining models to do one-time decisions, because they're not designed for that in most instances, it's hard not to think about those things when you're making a decision. It's hard to just think about the big masses and not about individuals that are being affected. So it's good to wrap your head around that and try to think of the psychology of customers. And you may, in fact, if you're trying to present a model to managers to implement, what's their attitude towards risk and making mistakes? Because it's important to have a sense of what their values is like and whether or not they'll buy into this average idea. So this isn't a topic covered generally when we're getting into data analysis, but it's important, I think, in how you frame things when you're trying to sell your ideas, doing deployment. Think about how people think, individuals think about risk. So this is an experiment that's been frequently done. And you've got a coin, say a loonie. I'm going to flip the loonie and I make you a bet. I'm going to flip my loonie 100 times. Each time it comes up heads, I'm going to give you $2. Each time it comes up tails, you give me $1. You're going to take the bet? It'd be crazy not to. That you should make a pile of money. That the expected profit per bet, that I pay you $2 with a probability of 0.5. You pay me $1 with a probability of 0.5. Half the time it don't happen. So the average profit per flip of the coin is 50 cents. And so for 100 flips, that's $50 on average. I should have to pay $50 per student that takes on the bet. Now, some students will get actually more than that. Some of them are going to get less than that. That's the average then. Okay. Now, suppose I change the opportunity. Say, I don't have time to flip it 100 times. Let's just do it once. Okay. If it comes up heads, I'll give you the $200. And if it comes up tails, you pay me $100. Okay. It's got the same expected profit. In total, $50. Will you take the bet? Well, there's a lot of people who will say no. Why? They can't afford to lose $100. Okay. From their perspective, that it may have the same expected value, but it's got more risk in the second case. The first case, there's small stakes that are there. Think about the course. This course, I don't have a final exam with 50% of the grade. I've got 5 tests altogether with 40% of your grade. Okay. But if you mess up one test, okay, you had a bad day, you still got 4 other ones hopefully to make things up. Not like 50% final exam or 75% final exams I had for my first whole year math course in university. It's scary. A lot of risk associated with that. It has the same expected value, but there's a lot more risk. It feels like you're gambling. that there's a lot of research on the psychology of risk, not my area of expertise at all. That the expected value versus risk trade-off sort of thing in finance, it's a huge area of study. And that the way people build portfolios, make investment decisions, it's this risk return trade-off, right? But it's not just the risk bit, it's also the way we present the information. So suppose I'm giving you something that is you're not going to lose anything on this one. You have a 45% chance of getting $6,000, okay, but a 55% chance of getting zero. Or you can take $3,000, 90% chance of getting that, only a 10% chance of getting nothing. Both of them have the same expected value. You multiply the amount of money times the probability and so on. They both come out having an expected value of $2,700. Which one would you choose? My guess is you'd pick the 3,000. You're almost guaranteed to win it. So it's there's an expression called a bird in the hand is worth two in the bush. You're going in, you're trying to catch birds, or you're hunting for birds or whatever. Having one for sure versus a chance to get two. Most people would say it's better to have the one that you've got than take the chance to double that money. And you'll hear of betting instances, and there used to be a show on TV, Who Wants to Be a Millionaire, that you had to answer questions stage. Okay, now your prize winnings are up to $1,000. Will you bet to get it up to $2,000 by answering a question? If you get it wrong, you get zero. If you get it right, you get up to 2,000, and you get to try another question. But the questions get harder. That when you feel pretty confident with what you've got and the amount is substantial, many people will say, I'm not going to gamble, I'm going to pick my money. So here's a different one then. Suppose the probability of getting the 6,000 is only 1 in 1,000, 0.1%. And the chance of getting the 3,000 is double that, but that's only 2 in 1,000, 1 in 500. Again, both of them have the same expected value. It's about $27. Anyway, which one would you go for? I can probably guess what you do. You're going to gamble. You don't think you're going to win at all. And that a chance of 1 in 1,000, 1 in 500 is small, but playing the lotto. So you'll gamble on the bigger prize. That's the motivation behind lotteries like Lotto Max and Lotto 649. People aren't playing the lotto to get a free ticket or to get $25 or something like that. They're playing the lotto to win the jackpot. And the chance of that is very, very small, but if the jackpot's big, millions of people buy tickets, that they'll gamble on that big win. And so if the payoff is substantial and the probability is quite high, then you'll go for the one that you're more likely to win. If the probability is really low, you gamble on the big payoff. There are other types of things, other experiments that have been done in the way we present information to people and what they will take and what they won't take. And it gets complicated. You can start understanding some of the psychology of the way things are phrased. It's even sort of like some of the multiple choice questions where students find it harder when I ask you which of the following is incorrect versus ask you which of the following is correct. that generally people do better if I ask it in the positive than in the negative. That the same way when we're phrasing different scenarios, if you're framing it with the emphasis on the positive outcome, you might get a better response than if you phrase it with emphasis on the negative. These are things that are important for what we get into next, which is deployment. And so you built your model, and now you're trying to convince others to adopt it. And that is part of your implementation. There's no sense doing all that work and then having your solution not be used. Okay. And you need to understand your audience when you're selling something, you're doing a presentation. And when you're doing a presentation about stuff to do with data mining, you have to understand your, or at least be sensitive to the differing risk attitudes towards risk among the decision makers that will be using your model. And how you explain risk to them is very important. Okay. So anyway, back to this with evaluation, something you should be doing on a continuous basis. Are you on time? Are you on budget? And are the objectives still the same? That is this still something that you should be doing? That you should be evaluating the process that you've used to get to this conclusion. Okay, because you're going to do future projects, and are there ways you could do those future projects better than this last one? It is hard to do. That with models, we're trying to evaluate them in terms of meeting our objectives. That's generally in terms of how accurate our predictions are, and you have to have a measure of what you see is going to be. With classification models, that becomes very complicated. It's not simple to define what's performance. It's much easier to define performance with value estimation models. People are much more at ease with that. That with repetitive decisions, we may be able to fall back on what's average performance, and that we may be able to justify our model based upon that. Not always can we assign dollar values to the outcomes. If you can, it's quite good. That, but the risk that you run into, particularly with expected value models, where you're looking at averaging things, and we aren't all consistent in the way we make decisions involving risk. We are not rational very frequently. And that you may be saying that, yes, it's a good idea for everybody to get vaccinated. That will, if everybody was vaccinated, then the disease won't spread. And making decisions about yourself. Oh, I don't put myself in risky situations, so I don't need to get vaccinated. I'm not going to hurt anybody. That I don't need that. I think vaccination is risky. If you said that type of thing, you're almost contradicting yourself. But people are actually, we did hear that repeatedly, that the difference between is what's best for society's own versus what do you feel is best for you as an individual. And that maybe what was best for everybody did have negative implications for some people. So how do you deal with that? I don't know. But you need to be aware at least of that challenge. And I don't think through the pandemic there was enough thought at times in the communication that came in from public health about the difference between those two, and seeing it from those different perspectives. It's challenging that they may have been making the right decision, but they may not have been communicating it effectively and conveying information to address concerns people had appropriately. So you've really got to change your language of presentation to minimize confusion and the complexity of it. It is very complex. And I think we're out of time. Okay. Oh, what are we doing next? Okay, if you show up to last week, because some of you won't need it, really. that you've accumulated enough points to get the grade you want. But it is important, it's bringing closure, that we have a tendency to teach you how to solve problems, but we don't teach you anything about implementation of it. I'm not going to get into the implementation, but I'll try to give you some guidance on presentation, how to communicate your findings. And it's the communication thing. So we've gone through different tools to help the data speak to us, get the information out of the data. Now we've got our findings. How do we communicate it back to the people that will be making the decisions? They're going to be using our results. So communication is the data talks to us, then we've got to talk to others. How do we talk to others about stuff we have analyzed all this data? And that's what we're going to try to look at next week. And that's the end. Thank you very much.